This is Lab 3 for Physics 2211 on black holes. In this lab, we analyze a given set of data to find the mass of a black hole. The data is regarding the position of a star as it moves around a black hole in the center of a galaxy. We can analyze this position data using a number of ways to get to the rate of change of momentum with regard to time, and use that equivalence to the net force to solve for the mass of the black hole using Newton's law of universal gravitation. At the end, we find the mass of the black hole to be 2.19 times 10 to the 31. Now, for reference, that's about 22,000 billion kilograms. Now, how do we go from knowing position data to discerning forces? Well, we start from Newton's second law, our fundamental principle in this case. It states that the change in velocity is equal to the net force divided by the mass times a change in time. Now, manipulation of this, taking m over to this side, which is coincidentally equivalent to the change in momentum, because mass times velocity is always momentum, and using further algebra to get delta p over delta t is equal to the net force, and for a small enough delta t, this approximates dp dt, the calculus term. Through this method, we find that the net force is equivalent to dp dt, which will be recurring through this lab, and is useful because we can determine dp dt using the data given. We do that in the same way that we reduce that formula to begin with. Delta p is the same as the mass times delta v, and delta t approximates dt when delta t is small enough. Now, since we know all of the variables on this side, the star's mass, the change in velocity, which is just v final minus v initial, which in turn is defined by the final position minus the initial position, and delta t, which for all of our measurements was 1 day, or 86,400 seconds. Because we know all of this data, we can approximate dp dt for each time interval. And once we find dp dt for every time interval, we know the net force for every time interval. At this point, we can solve for the black hole's mass, but we should rather refine our visual model so we can see what exactly is happening in the system. We do this by defining dp dt parallel and dp dt perpendicular. The parallel components of dp dt represent speed changes, and the perpendicular direction changes. Now, each of these are respectively equal to the parallel and perpendicular components of the net force. Now, it's important here to realize that though the net force and the change in momentum are mathematically identical, they are not exactly conceptually identical. The net force is an unseen cause. Likewise, we can derive dp dt from observed data, but we can only infer the net force. It's only because of our fundamental principle, Newton's second law, that we know these are equal. Put more succinctly, we can't observe net force. We can observe change in position with regard to change in time. Now, this same principle goes for dp dt parallel and f net parallel, and dp dt perpendicular and f net perpendicular. This is important to keep in mind as we view the simulation. What we know is the star's position. What we are calculating, and what we find out after the fact, is all the net force along the way. In this model in particular, we can see the net force, which is always pointing towards the black hole, and f net perpendicular, which changes its direction in this ellipse, and f net parallel, which is currently slowing it down. Although, of course, these arrows change as the simulation runs, getting very large when close to the object, in accord with the gravitational force, and getting a bit smaller as it goes farther away. Again, our simulation is an analysis of data, not a prediction. Nevertheless, it does help us visualize the situation and give us important context for the physics. The black hole and the star are attracted to one another via gravitation, the force of which is mathematically related to the mass of the larger object, the mass of the smaller object, and the distance squared. Big G here is the gravitational constant that makes sure all our units work out well. Also, because our star and black hole are the only objects in the system, the net force on each of them is equal to the gravitational force. This is important because in this equivalence, we know the magnitude of net force, we know the mass of the star, we can find the distance between the star and the black hole, and g is just a large constant. So we only have one variable, m, and we want to find m, the mass of the black hole. We can do that by using some algebra to get everything in the right place, and we find, as stated before, that our mass is 2.19 times 10 to the 31 kilograms. Now, as I've been stressing, everything that we've just figured out comes from what we know. That is, the data set that tells us the star's position. So what if something changed? Something fundamental to the system. Like, what if the black hole itself was instantaneously swapped out with an identical black hole? That is to say, all of the forces are unchanged, so the motion is uninterrupted, and the general elliptical orbit will also be unchanged. Would we be able to know? Could we tell from the data that's given us? Well, the motion is our entire source of knowledge. The motion, change in momentum, and the implied forces all work out to suggest an elliptical path around a very massive black hole, but we can't ever really know for sure. But this shouldn't come as a surprise. We're observing the star move around. We aren't observing the black hole. We can't. It's black. It doesn't emit light. So, in sum, if the black hole was instantaneously swapped out, with no change to motion of the star, then we couldn't know. However, this is obviously unlikely, because, after all, things don't just blink in and out of existence.